time to start then?
Yeah, please go ahead.
Right. So welcome everybody to this session 8B, parallel session 8B in the Circular Materials Conference. And this session is about phosphorus, the nutrient phosphorus. And I'm just going to give a very brief introduction before I start introducing the speakers. I'm going to share my screen to show you the schedule. Here you see a list of the different speakers that will be talking today. I'm Magdalena and I will be moderating this session. I will introduce each of the speakers and then I will also moderate the panel discussion that we will have in the end. And I'm a professor at Chalmers University of Technology, and I work with life cycle assessment of, among other things, phosphorus recovery, wastewater and sludge management. We have a very strong focus on phosphorus recovery right now for various reasons, of course. As you all know, phosphorus is a very important nutrient. Basically, all biomass production is highly dependent on the access to phosphorus. And therefore, phosphorus also creates problems when it ends up in the wrong parts of the environment, giving rise to eutrophication. But because it's so important, it's also important that we have a constant access to phosphorus. And then we're concerned about the depletability of phosphorus resources. We're also concerned about the security of supply with some of the mined phosphorus available only in very geopolitically sensitive regions. And then in our efforts to bring phosphorus to biomass production sites, regardless if it comes from mines or if it is recycled from other biomass production, like with the sewage sludge, there is a risk that it brings contaminants. So there are so many interesting aspects related to phosphorus and so much need to assess this in various ways and to discuss how we solve it on a societal level. And just as a very brief introduction, I'll throw in two things from my own research that puts this a little bit into perspective. First, I'm going to show a study, just one piece of result from that study. It was a material flow balance that was done for phosphorus for Sweden and the Swedish economy. And the question we asked was to what extent we can create a circular economy for phosphorus in Sweden. Is it possible? And then what I show you here is what we found for agricultural biomass production. And basically, this is then the current situation. These are the sources that we put today on our agricultural soils in Sweden. And if we, for example, then would like to make ourselves less dependent on mineral phosphorus input, this part, then what sources do we have to access? And some of those things will be discussed today. One thing, several of the speakers will actually be talking about mining waste. That's a huge potential source that could bring a lot of phosphorus. And some of you will also be talking about various, renewable sources, we could call them, how to recycle sewage sludge and other sources from cities to agriculture. And they bring less, but they can still bring very important contributions. And there's a very strong ongoing discussion now on various possibilities to find new sources and to cycle them or bring them to agriculture or other biomass production in a safe way. And I just want to show you very briefly that we have an ongoing project on dairy industry for phosphorus recovery right now, where we look at the possibilities to recover phosphorus from dairy wastewater and dairy waste and bring that to agriculture. So it's not only sewage sludge, there are also, or mining waste, there are many other possible industrial sources that we could also think about. And I think we will probably hear about some of these technologies that we today, that in that project we consider for dairy processing waste, but those can also be interesting for other sludges or wastewaters and things, as we will, I'm sure, hear today. So I'm gonna stop sharing my screen here, and I'm gonna, let's see here, bring in the first of the speakers. And it's Ulrika Håkansson from LKAB, and she will talk about a Swedish source of critical minerals from mining waste. Welcome, Ulrika. The floor is yours.
Thank you. Thank you. And now you can see my screen. So thank you very much.
Perfect.
So yes, I'm Ulrika Håkansson, and I'm a business manager or business manager in the division of special products at LKAB. So I've been part of creating new businesses from other sources than our iron ore. As you know, LKAB is the largest iron ore producer in the European Union. We stand for about 80% of all the iron ore within the European Union, and we produce almost 30 million tons of iron ore yearly. But we also have an important industry in the minerals portfolio, and that's where I belong. LKAB is now part of a major transformation to be carbon dioxide free, and also adding the product line in another step in the value chain. So we're going to be carbon dioxide free, and we're also going to produce sponge iron instead of the traditional pellets that we've been done for decades now. So we're creating that one. And the other part of the strategy is to extract critical minerals from our mine waste. And that's where the project I'm involved in or leading right now comes in. So I'd like to start with an introduction about that project, and by showing a video. And I think I will have some help with that. So please show it. It's about 2-3 minutes.
In our everyday life, minerals are all around us. Some we're hardly even aware of, like fluorine in small medical applications, or neodymium in magnets for electrical vehicles or wind turbines. With a growing population, the demand for minerals is higher than ever. At LKAB, we have accepted this challenge. These critical raw materials that we need come from down here. And through new technology in the REMAP project, we aim to prove that mining waste can become an important asset to the world's needs, without emitting unnecessary carbon dioxide. By establishing a large-scale industrial park and using innovative technology, we will extract valuable resources from the tailings sand. Rare earth elements, gypsum, fluorine, and perhaps most importantly, phosphorus. Without it, global agricultural production would be halved. All of this will be produced with fossil-free energy, such as hydro and wind energy, something we have in abundance up here in the north of Sweden. We can't single-handedly solve the world's need for critical raw materials. but this will certainly make a very important contribution. LKAB already operates some of the most climate-efficient mines on the planet. But now we're starting yet another ambitious journey to turn today's waste into tomorrow's resources.
So I'm going to share my screen again. So here we are. So thank you for that. So just to get a sense of the volumes that we can create by this project, it's about 30% of the European Union's need of rare earth. And today we have no raw material source within the European Union today, so that we would therefore be the first in that case. When it comes to the phosphorus, it's about 5 times the Swedish need of phosphorus mineral fertilizer. So it will be a great opportunity and a great contribution to the European Union in terms of the phosphorus need. And it's about 80% of the European Union is imported today. So that we can be a significant change there. So we can reduce the dependency of import and increase the security of the supply chain of these critical minerals that are on the critical raw material list, as you know. We also have other ambitions than just delivering these products. It's that we will use production methods also in part of the larger LKAB scale strategy. We also aiming for the fossil-free production method, so we can have a really low carbon footprint on the final products. We want to make sure that we can kind of productify as much as possible of the apatite that we will use in this project, and make sure that these are commercial products and that they are clean when it comes to, for example, cadmium, when it comes to the phosphorus and other sources that can be not good for the phosphorus products. We also want a high grade version. We're going to use a lot of electrification, of course. As part of also the LKAB strategy, we're going to use a lot of hydrogen gas even in this project to make sure that we get a footprint good for the products. And by this, it's going to be a large-scale industry. That's why we're talking about this industrial park, because it's not just one plant, it's several. So it's hundreds of jobs, and it's a substantial investment for LKAB. So how is this plan to work? We start by the mines, of course. The mine waste, the fresh tailings from our beneficiation plants in Kiruna and Malmberget. There are large volumes, so we do a first flotation plant in both places, and with a flotation method we can create an apatite concentrate that can be transported by train to the industrial park. So the first concentration part is done by the mines. After that, we go to the heart of the project, or the heart of the industry and the industrial park, and that's the hydro plant. In the hydro plant, we create the product or extract the products from the apatite mineral. So we create a fluorine product. We create the rare earth elements like a concentrate. So that's how we're going to an oxide concentrate for further development downstream. And a clean gypsum that we can use for the construction industry, plasterboards, etc. That type of products. But of course, the main part is, or the main focus, and what we're focusing on is the phosphoric acid that we're going to produce from the hydro plant. And from the phosphoric acid, we can produce the mineral fertilizers to the final products and our main product. In this area, you also see two more plants, and that's the two major feeds that are needed for the hydro plant. It's the sulfuric acid. That's really essential for the run of the hydro plant. We mainly see that from a cost control perspective, and it's also adding energy as its type of production, so we can use that energy, so it fits really well with the industrial park to reuse the energy there. For the ammonia plant, it's all about the carbon footprint, and that we also have good access for the hydrogas, so we can produce green ammonia and make sure that our fertilizer has a really low carbon footprint. Ammonia, green ammonia, it's about double the cost of so-called brown ammonia, so it's not so it's sensitive for the business case, but we see that essential when it comes to the whole scope of the project at this point. We are in a pre-study phase, so we're working a lot with the piloting and that type of things to verify the processes. We have done most of it, and so we're going to have our pre-feasibility studies, as we call them, by the end of this year, so we can make a good decision how to move forward for the basic engineering and taking a board decision. So that's where we are right now. We have done also a lot of exploration, so we know that we have the phosphorus source with us for the whole lifetime of the project, and LKAB has done a lot of work there. So we know that until 2060, we will still have it in our fresh tailings. Apart from that, we have a source in our tailing dams. In this project, we haven't taken care of the tailings dams yet. So that's to come on the next phase when we hopefully succeed with implementing this project. So we do have a large source with us in LKAB. Our main focus, of course, being on process development on the hydro plant. That's where we make the difference from the state of the art by extracting all the products and not only the fertilizer one. We estimate approximately to be up and running by 2027. It highly depends on our environmental permits. We need new permits both in Kiruna and Malmberget, and we also need it for the new industrial park. So there are 3 permits, and it's especially the one by the mine that are on a scheduling critical path, so to speak. We also need a lot of electricity, of course, especially the ammonia plant is very consuming when it comes to electricity, even though we have the sulfuric acid plant delivering some of it. Financially, we can see on the market side that, of course, especially with the ammonia side, we have a higher cost than kind of the low market, the other markets, or the state of the art. But then we don't have the other back with that. We don't have a gypsum tile that can't be used. We extract the REs, so we do see some. But we hope that we can see some sort of market premiums or demand for these type of products moving forward, so to speak. So we have a project website where we update our status of the project and news what's happening, and so you can see that on our remap.com, and I hope you can contact me if you have any questions, and thanks for listening. Thank you.
Thank you very much, Ulrika, for this very interesting presentation. You said that one way to get your questions answered would be to contact you.
Yeah.
Another way would actually be for people to write in the chat, and then I can bring them up in the panel discussion later on, because we have some time after everyone has finished. So we won't take questions now, but do write in the chat and we will try to get back to them when we have the panel discussion after everyone has presented. Thank you so much, Ulrika. Really interesting to hear. Our next speaker is Erik Kärrman from RISE, and he will talk about, give us an overview of the status and future perspectives of nutrients recycling from sewage in 9 selected countries. Erik, the floor is all yours.
Thank you very much. Can you see my presentation now? Hello everybody, my name is Erik Kärrman. I work for Research Institutes of Sweden and I'm a director of the unit Urban Water Management. And I would like to give a presentation today about a project that we did a couple of years ago, where we did an overview of the status and future perspectives on nutrient recycling from sewage in 9 selected countries. This study was initiated, as I said, 2 years ago, 2019, by the governmental inquiry in Sweden, which was about sustainable sludge management. And you can also see the title of it. But our study was a report to them, and it was financed by Sweden's innovation agency, Vinnova. This work is also fully reported in a report in Swedish, you can see here. So it is available online. What kind of methods did we use? We were selecting these 9 countries, and the focus was, of course, what should we do in Sweden in the future? So it was countries with similarities to Sweden from different perspectives. So it was more or less European countries, but we wanted also another country to give perspectives on that. So we also have Canada as one of the 9 countries selected. And we were gathering information from different sources. We were doing interviews with typical national experts or coordinators in this field for each country. We were using statistics from Eurostat, and we were looking at literature and web-based information. The typical topics we were investigating was main management of sewage sludge and phosphorus extraction today, expected future management of sewage sludge and sewage recycling of nutrients through sewage in a 5-10 years perspective. Specifically, also we were interested in nitrogen extraction, since that has been more on the agenda the last years, not only phosphorus, but also nitrogen. So therefore we try to investigate that a little bit deep in depth. And also we looked at experience of source separated sewage systems, since that is an interesting way of recycling a lot of nutrients, not only nitrogen and phosphorus, but also other nutrients. We looked at natural targets, regulations, and different instruments to promote nutrient recycling from sewage. We also looked at ongoing research and development activities. And here we have a typical image of how it looks more or less now in these countries regarding the use of sewage sludge. First, we have some 3 countries with a lot of red here, and that's incineration. They are using a lot of, they are incinerating a lot of the sewage sludge in these countries, Germany, Netherlands, Switzerland. And then we have two countries, Sweden and Finland, where is actually historically we have been using sewage sludge to other uses. Mostly, okay, we have quite some use at agriculture as well, but most of the sewage sludge has been used in soil production and used for covering of landfills and more technical soils for infrastructure projects and so on. And then we have some countries, Denmark, Norway, and Great Britain, where a lot of sewage sludge is used actually in agriculture. And finally, Canada, and we actually looked at one state in Canada, Ontario, and they have a mix actually of both recycling and using it's sewage sludge and incineration. What we did when we tried to categorize these countries a little bit to talk about them in groups. So we said that we call them the legislation category, Germany and Switzerland, the investigation category, Sweden and Finland, and the threshold limit value category, which are the remaining countries. And what was typically for the legislation category was that they have a ban for use of sewage sludge in agriculture in Switzerland since 2006. And in Germany, there are strong regulations since 2018, where they should have a very clean phosphorus recycling plan, actually. So, and it's a limit of regarding the size of the treatment plant. So it's from 50,000 and bigger, where we have very strong regulations for this. So it's very much a domination of incineration here, but they have quite large ambitions and also starting some activities to recycle phosphorus in these countries from the ashes. Then we have the investigation category, typically Sweden and Finland, who comes from the situation where we have used alternatively the sewage sludge lots. And there's a quite large debate, for instance, in Sweden, how to go further on. And we had this inquiry who was actually supposed to suggest the legislation to ban sewage sludge on farmland. But they did that, but they also had another opinion also presented with other types of recycling, actually, of nutrients. So both have quite some ambitions to go for more recycling of nutrients, and Finland more through policies. They would like to be front runner with nutrient recycling from sewage from different perspectives and take it that way. And Sweden had this suggestion of legislation, as I said, and the question is whether this will be a reality or not. Not sure yet. Threshold limit value category, they use a lot of sewage sludge at this moment in the agriculture, and they have actually no concrete plans to change this. This seems to be a running activity that will remain, actually. And we also put Netherlands in this category, and they are quite different, definitely because they have strong regulations if you would like to use sewage sludge on farmland, but there are other circumstances, I would say, that is more important here, and I will come to that now, because there is a lot of other factors than what kind of threshold values you have or policies, because Netherlands is it's a very much an agricultural country, and they have a lot of manure, So the drivers to use sewage sludge is very low. So there are, of course, other factors that affect this a lot. And we've seen that there are other things that make this big change between different countries. Attitudes to incineration, for instance. It seems as a quite popular thing for Germany, Switzerland, and so on. But in Great Britain, it seems to be very, they seem to be very skeptic to go this way, so to say. And there are also, of course, the possibilities of alternative use of sludge, as we have in Sweden, for instance, that affects the market a lot. We also looked at nutrient extraction in wastewater treatment plants, and it's not, it's a lot of things going on, but it is not at a full-scale perspective. There is not very much actually, but there are both, of course, true white production used, applied in different wastewater treatment plants, and also nitrogen recycling, but it is a little bit marginal, I would say. We also looked at source separation system, and it's very interesting to see that in both Sweden, Germany, and Netherlands, there are quite new built areas. Here is an image from Helsingborg, Sweden. So we will get a lot of information about this soon, because they are new built and just yes, so there will be new information about this, which is very interesting. But it's of course a marginal thing looking at whole Europe, so to say. It's only districts in a couple of cities. So what we found here in this study, more or less, to summarize, was that the movement towards incineration of sewage sludge, with possible extraction of phosphorus and possible use of agriculture, is something that is growing actually in parts of Europe. But at the same time, we have a more or less an unchanged use of sewage sludge in other parts of Europe, and they seem not to be interested in change this. We have a lot of interesting ongoing research, pilot studies, and full scales in different ways of recycling nutrients, source separation systems as well, which will be interesting to see the outcome of that. But we also see that there's a lack of business models for the circulation of nutrients from sewage to agriculture. So there is a lot of work needed to be done there to if we would like a cycle here. I think I will stop there. Thank you very much.
Great. Thank you very much, Erik. Very interesting to hear, and fascinating that there is such a big difference between the different European countries. We might get back to that in the discussion later on, but let me now then bring the next speaker to your attention. It's Lisbeth Ottosen from Technical University of Denmark that will talk to us about recovery of metals and nutrients from ashes using a certain technology. So Lisbeth, the floor is yours now.
Yes, thank you. I think you can hear me, but I'm not allowed to show my start. Okay, I guess you can see me now, can't you?
Yes, I can see you now. Good. And I think Andre is also now spotlighting you. So perfect. So go ahead, Lisbeth.
Yeah, I just need to share my slides also. I think it's not really working.
Do you have this green button?
Yes, I do, but
down.
it's not.
And then you can choose what screen or presentation that you want to show.
Yep, but it's not allowing me to share anything. Okay, now we go. I think. I see my screen now?
Yeah,
yes.
We can see it also.
Ah, that's
and now
perfect.
you need to put it in presentation mode as well.
So, thank you, and sorry for this small delay. And thank you for the introduction. I'm so happy to be here and in this very interesting session to give this presentation. I'm a professor at the Technical University of Denmark, and I will today talk about recovery of metals and nutrients from ashes using electrodialytic extraction. First, a bit on where
Lisbeth,
I'm from.
can I just interrupt you and ask you to try to put your presentation in presentation mode so that we can see your full screen?
Oh, it's not, because it is for me. That's a bit...
Okay, it seems that you shared only PowerPoint. Could you please reshare? I'll stop your sharing. If you could please reshare and try to share the whole screen. Select the desktop one or screen one, either way. It says an
entire screen.
Entire screen, yes. Then the presentation mode will work.
Sorry.
And now go to PowerPoint. Yep. From there, yeah, and now start, yeah, from there.
Is it working now?
Perfect, perfect.
Okay, then you got a full view of my working place when it's not Corona time. And this is the Department of Civil Engineering, where I'm, as I said, a professor, and I'm also heading a section for materials and durability. Since I'm at this conference now, and maybe it's not the audience in this small group here, but I would tell you that in our department we have a focus area. We have 3 focus areas, and one of them is actually circular civil engineering. So there's of course a lot of interest from my side in many topics of this conference. However, now it's about phosphorus, and how did I get there? Well, I do have a research group where we're working on resource recovery in a holistic view, and that means that we would like to use all the resources which are retained in different, now today, waste products. And as you are aware of, today it's about sewage sludge ash, and I'd like to tell you how we see a possibility on transforming these ashes to resources by a method called electrodialytic separation, which we have developed. And here it is, as I said, sewage sludge ash as an example. And the overall idea is, yes, well, we take the sewage sludge, and as we just heard in the previous presentation, we incinerate quite a lot of it in Denmark, and in some countries, all of it. In other countries, like Sweden, not anything, but it might come, you never know. And we get energy out of incinerating it. We have a very modern, 2 very modern plants in Denmark where they actually gain energy even from incinerating such wet products. And then they also get the sewage sludge ash out of it, and it is what you see here, the red powder, that is sewage sludge ash. And today it is mono-deposited or sent, or there are other plans for it, but it is right now just not being really recovered. So what we suggest is that we take a look at this. There is a lot of phosphorus in it. There is a mineral material, which could also be a resource, and then we have heavy metals, which we learned yesterday that, for example, copper is a really critical raw material. So such sewage sludge, as you can see some of the major components here, it's quartz, then we have hematite, that's why it has this nice red color. Then we have white locite, which is a phosphorus product, and there's also some calcium carbonates. And below here, you can see I put some concentrations. It is in these ashes that I've been working with and show you results from. We have quite high phosphorus concentration. You can see up to 10% can actually be phosphorus in these ashes. So we are talking about grams per kilograms here. And then I also listed 3 heavy metals, zinc, copper, and lead. And you should notice here that these are in milligrams per kilogram. So it's really, there is a scale in difference in the concentrations in these 2. But with this high concentration, we could, or we should, possibly mine the phosphorus out of this sewage sludge ash. You can extract it in acid, the phosphorus. That is what I show here. Here I just have had different concentrations of acids. It's getting higher and higher concentration, lower and lower pH to the left here. And then I have shown here how much I've solubilized of these elements: phosphorus, black, and then copper, zinc, and lead. And as you can see, if you go low enough in pH, here it was about 1, then you have almost all phosphorus extracted. But what you also see is that you will also extract the copper, zinc, and lead at the same time, at the same pH. It's unavoidable if you do it like this acid extraction, and therefore you need a separation step afterwards. What we suggest instead is to do it simultaneously. And you can do that, simultaneous extraction and separation. And you can do that if you apply an electric field, use an electrodialytic method, like I'm going to show you here. Not that many details. You're much welcome to ask me about details later, but due to this short time, you just get the fast version. You must imagine here in this compartment, I have two compartments, as you see. In this compartment, oh, how very in this compartment here, I suspend the sewage sludge ash in water. Then I have another compartment here. I place the cathode in the other compartment, that is the negative electrode, and over here it's a positive electrode, the anode that is placed. And then I have something here which is called a cation exchange membrane, and it's a membrane that only allows positive ions to pass. And when I then apply my electric field here, from the electrode process at the anode, I will have acidification. So that means that my acid is produced by electricity directly into the suspension. While it's acidifying, we will have a release of heavy metals, which are in the electric field transported into the cathode compartment. And then the phosphorus, as it is negatively charged or in uncharged complexes, it will stay in solution here in the suspension of the ash. So this is the separation. We have the phosphorus here in the suspension, in the liquid phase, and then we get the heavy metals out here. So let's see if it works. So these are, here you can see the primitive cell. The green color in the graph shows that this is what is in the solution at the anode compartment, and the red one is what left the solution here into the cathode compartment, and the black color just shows what is left in the ash. So we can first see that very little phosphorus was left in the ash, and 80% of it approximately stayed in these experiments here. It's 3 similar experiments, that's why there's an error bar. And in these experiments, 80% of the phosphorus was in the suspension here after the experiment. We could see I lost some phosphorus, and this is an optimization. We've optimized it a bit since then. The longer you run your experiment, the more phosphorus you can potentially lose. So this was, we can go below 10%, but you cannot go to 0. And lose means that it went together with the heavy metals. And then you can see that the red colors for especially zinc and copper, they show that we have a very good separation of these heavy metals onto the cathode compartment. Lead is bound more hard into the ash, so most of the lead actually stayed in the ash, even though we reached pH of 2 in these experiments. What you should also remember was that I talked about grams per kilogram for phosphorus and milligrams per kilogram for heavy metals. So it's not like we have almost as much, that we have 10% of the per weight of the phosphorus was the same as we had, for example, for lead and for the heavy metals. There's much less heavy metals than we had phosphorus in this suspension. So let's now take a look at the different things that we have separated the sewage sludge ash into. And first we can look at the suspension where we have the phosphorus. Now it's filtered. And in order, actually I did this, I wanted to measure the cadmium content, and it was simply so low, so I had to evaporate the water and concentrate it very much. And then I wanted to solubilize these small crystals again to see how much cadmium I actually had. But then when I saw it, I took this picture with my mobile phone. I just immediately thought that this could be a good picture. So this is these crystals were, you could say, the product. This is the concentrate of what we could get, most concentrated fraction we could get out of this solution. And we went to the SEM to see what's actually there and took some spot analysis. And most of it is like we wished for. It's phosphorus, there's a little aluminum, there's a little of iron, and then there's also calcium in it. So it is a mixture of calcium phosphate, this calcium phosphate and phosphoric acid that we have here. And these are very good products to continue with in the industry. Calcium phosphates are soluble, so you can easily get your phosphorus out. Maybe it's not the right way to concentrate your phosphorus to evaporate the water, but this is a way you can do it. And then, as I said, I wanted to know what is the cadmium concentration related to the phosphorus concentration. And as you can see here, it's really low. It was 3.7 milligrams of cadmium per kilogram of phosphorus in these crystals here. And it is very low compared to commercial fertilizers. And these, for example, in Europe has an average of 138 milligrams per kilograms of phosphorus. And the concentration we obtained was actually in the very low end. I think maybe it was at the lowest end of what I could find in literature on the commercial fertilizer. So it is a very clean product that we have produced here, a clean phosphorus product. So what about the heavy metals? They were much lower in concentration, we remember that. And right now it is probably not feasible economically to concentrate these, but I would like to show you what happens to them and like to show you what could possibly happen. The first in the table here I have, you can see the concentrations that I had recovered, and it says grams per ton, and you know, I should maybe admit that I have maybe 100 grams in here, so it's not that I had recovered half a kilo of phosphorus. This was calculated until grams per ton. And what happens to it when I do my electrodialysis, it was that it goes from the anode compartment to the cathode compartment, which you see here. You can look into the end of the cathode compartment here. A cathode, you can see here that it is just a rod which is sticking into the compartment. And then you can also see that it definitely gets thicker when I do apply my electric field here. And what precipitates here, it's a lot of different elements together. There's a lot of aluminum, there's also calcium here, and then we have copper. Is almost all copper is precipitated here. Zinc precipitates to some fractions and so forth. So this is a mixture of everything. But it is very interesting that you can have it, it's highly concentrated here. And if you're very smart and bright, you can actually use this electroprecipitation to get products like this. This is pure copper. 98% pure copper. It is not extracted from ashes. I should admit it immediately. That's why I put it here. It's something I have actually extracted from polluted soil. But you could say here that this is the idea. This is what we would like very much to do with the heavy metals. We would like to have them like resources like this, pure resources which can be used directly into the industry again. We are not there for the ashes or for the sewage sludge ashes, but it can be done, shown here by examples from polluted soil. There's almost half a kilo of copper here actually, so it's not just a small sample. But we still have something left. We still actually have an ash. It is still very red because iron oxides are not very soluble in acids. And about 50% of the mass is left after I've extracted now the phosphorus and the heavy metals, as you saw. So we ask ourselves, and as I said in the beginning, I'm from the Department of Civil Engineering, so that was a question which we could answer ourselves. Could this actually be a possible resource in construction materials? And therefore we tried to cast, I've had a PhD student working on this, therefore we tried to cast concrete with this ash as a cement replacement, and that's a good story to replace cement because cement is producing, cement production gives a very high CO2 emission, and it's actually 5 to 8% of the anthropogenic release of CO2 to the atmosphere is actually due to cement production. So can we reduce this by using other things like sewage sludge ash? We are really on the good environmental side. And what I show here is that the concrete, this is concrete without any type of ashes, it's normal plain concrete. And then when I mix in my sewage sludge ash, which is treated, I get the nice colors here on the lower row. If it's not treated, you get the colors up here. It cannot be used directly. It needs to be milled, so it needs to be processed in some way. But when it is milled, you get a nice color, and you can actually replace 20% of the cement without losing losing strength of the concrete. So this could be a very good solution for this treated ash. It could also be used in bricks. Here in Denmark, we have a lot of brick houses. We like very much to live in red houses. I do not. I live in a yellow house, but it's not very, most people will like the red houses. But actually, it is a scarce resource, the clay that you incinerate, you fire and get red bricks. You get yellow bricks in the brickworks right now. But if you mix in a bit, and this is 30% of the clay is now replaced with sewage sludge ash, and you can see you get nice red color again. And it also had good qualities. These bricks, brick pellets, it was I made here. So that could also be a use. So there could also be a use for the mineral fraction after extraction of the resources, elemental resources. So in summary here, we have the sewage sludge ash and the electrodialytic process, and we produce phosphorus for the fertilizer industry. Hopefully in future, we also produce heavy metals for other industries. And then the mineral residue could go to the construction materials. And then there's very little left which is not recirculated. And the little which is left could be either mercury and cadmium, for example, which we simply need to get out. But it would also be a very high benefit to get these out of the cycles and simply deposit it in the most safe way at all. So all resources that could be used are used by this process. And my final slide will be, what is the next? Well, we are trying to upscale now the process. You have a picture here. It's just, we just made this design, and I hope I'll come back and maybe and talk at this conference next year or the year after on how we progressed on this. That can be 3 to 4 kilos in this tube here, and it's made from a totally other design. So it's, I guess, also another presentation. But this is ongoing work that we are upscaling it, and we are doing this together with Biophos, one of the, well, the player on the market for incineration of sewage sludge ash in Denmark. And then I also put over here, you can see to the right here, I put a line on municipal solid waste incineration fly ashes, because we're also working on these, and it's not so much phosphorus, it's more heavy metals and other scarce elements. It's the same process. It's another material which is much more difficult to work with, because it's we have the whole periodical table here, which we could extract. So there's a lot into it, but we aim for this one. We also aim at ending up, as I showed you before, with pure copper in this case. And now that we had the first presentation, I was a bit annoyed, because of course I should also have put mine tailings there, because we also work with mine tailings. Even though this presentation of mine was about ashes, I could say that we can do use exactly the same process and the same things, the same knowledge, more or less, and then we can also mine tailings by the process. So this was all from me. So thank you very much for your attention, and sorry for the troubles in the beginning of my presentation. Any questions, you just send me an email.
Thank you so much, Lisbeth. Very interesting to hear. There's so many interesting technologies being developed right now. So I'm really glad we get to hear about some of them at this conference. And now then over to the next speaker, and you mentioned mine tailings, and I think we will hear about that again, maybe from Christer Lindqvist at Grängesberg Exploration Holding AB. He will talk about the Grängesberg Apatite Project and give us an update on what's going on there. So welcome to the session. The floor is yours.
Please unmute your microphone, Christer.
Of course, it's easier then. Thank you very much for having me. It's a pleasure. It's interesting to listen into the various new technologies, and we are a company, and I will share the screen now, which are moving into the let's see here, share, right? Like that. Come on. Does it work? Right?
It works fine.
Yeah, right. Also, thank you very much. Yeah. Well, I mean, we are a company, or commercial company, then working with proving technologies, and but also very keen on see what is coming downstream. Our, let's say, where we are and where we will leave our products. So we, and Grängesberg Exploration AB, Holding AB is a listed company in here in Stockholm on the Nordic SME, and we have some 7,000 shareholders. And what we do is we identify, acquire Swedish mineral projects which can contribute to the transition to a circular as well as fossil-free society. And our two first projects we are working with is the Grängesberg Apatite Project, which I'm going to talk about today, but also, which is more important, we also recycle mines, I may say, because we are getting into old mines also. And in this case, Dannemora, very old mines, 700 years of history of iron ore extraction. And here we are restarting that project ore mine again for production of a high-grade material or iron ore concentrate for the aiming to be a part in the future or the trend towards fossil-free iron making. So that's where we are. We are actually, hopefully, taking part in what's going on up in the northern part of Sweden with hybrid and H2 green steel and so on. So, but today is Grängesberg. Anyway, we are located in the middle of Sweden. Most of the mines in Sweden and the extractions are going on up north, but we are in the middle of Sweden, not in the middle of nowhere. We enjoy a lot of advantages due to that, due to logistic access to logistics, both rail and especially railroad actually. These are old mine sites. These are industrialized areas. So we are not in greenfield, not at least right now. And we enjoy a lot of support from the local and the regional society. And that's very important when you move into these kind of, let's say, permitting processes, which are absolutely necessary to be able to get on stream with production of and retracting the minerals and we are aiming for. So iron ore, the Grängesberg Apatite Project then is a recovery project of the tailing dams in Grängesberg. You heard about LKAB's plans and earlier today, and this is actually more or less the same. I would say Grängesberg is older than LKAB and the mines up there. Grängesberg as a mine was actually, a mining company was actually owning LKAB once upon a time in the early last century. This was also the largest iron ore maker in iron ore producer in the world in the early century, last century, 20th century. Anyway, so what we are targeting is the tailing dams around that old mine, which is now closed. Hopefully will come on stream again, but that's another project, different one. So we are targeting the first dam, which is the Jan Mats dam, and that's a sizable dam in our respect. Have a high grade of phosphorus in the tailings as well as rare earth. And we see this as our starting project for a much larger operations going forward. Life of mine in this case is 7 years and around 75,000 tons of apatite is the aim to produce when we're up and running. It will take some time before we get on stream, of course, because of the, well, predominantly due to the permitting process, which is lengthy nowadays and getting more and more troublesome, I would say. But anyway, we are located in Grängesberg, as I mentioned. We are focusing on the Jan Mats dam southwest of the village of Grängesberg. Grängesberg, to you all, I guess, are more familiar to you due to the Spendrups beer, and that's fine, and it's tasty and good. But we are focusing on the tailings here. And this is the site we are starting with. We have also expansion opportunities once we have exhausted the extraction from the Jan Mats dam. And there are three more sites around the Grängesberg village. And the dam as such has been in operations in the 1950s up to 73, where it was closed actually. And thereafter, Grängesberg Iron Mine Company started to extract the apatite as a byproduct from the iron ore making at the time, all the way up to 1989. So, so this is the last big I should say, dam with phosphorus in it, but it's enough to start with. At the same time, this happened, the LKAB was sold to the state, the last 50%, late 50s, and the money was used for various investments, also to build a new industrial plant very close to this dam. And this is how it looks today. And we have the industrial plant or area still there, and that's very fortunate for us, let's say. So we have the plant there, and we have the tailing dam just adjacent to that, and we have the marshalling yard just on the doorstep. So we have the internal logistics very easy. We can get to the tailings very easy, and we can also produce a sellable, exportable product and send it out with the rail down to the harbors, Oxelösund or Köping. So this is very, very fortunate and good for this project. There is a process plant there where we will fit the hydrometallurgy process, floating plant for extraction of the apatite. But without the going forward about what we are doing right now, because we are in a silent period and it's unfortunate. So I can't actually give you a very update on where we are in our process tests actually, but we are on high speed. We are developing a process layout now or flow sheet, which is very interesting and is using the latest technologies. We are conducting the process testing at the GTK in Finland in Outokumpu. But I can't give you the results because they have not been published. I'm sorry about that. But anyway, but we know that from the apatite process, we also, well, it has been known earlier that there is a lot of other, or at least two other rare earth minerals in the tailings. And they are due to the price increase, as we have seen lately on rare earth, as well as on the expected price increase of phosphorus from the customers or fertilizer producers. It is very interesting to start to extract or separate at least these kind of other minerals, and it's monazite and allanite predominantly. And what we see, what I can say actually, is that we see that we can produce a phosphorus mineral or apatite with very high phosphorus content. There is no cadmium in it, and we are low on arsenic. But the risk we have, and I come back to that, that is the permitting process. And that's the risk that we have larger delays than we should have. So that's where we are. But with the rare earth minerals and the additional contribution we can get from there, we also contribute to the European self-sustainability of the rare earths, at least a part, not as much as LKAB will be doing later on, but at least a part, and we will probably be on stream earlier than LKAB with their processes. So in order to contribute to our maintained lifestyle and not reduce the self-dependence on China, Grängesberg is a part of this how should I say, strive to supply critical metals and minerals for Europe. So with that, I think I stop and say thank you.
Thank you so much, Christer. That was very interesting to hear, although it felt a little bit like a teaser. So we're going to have to look for upcoming publications, right?
Yes, that's right. Absolutely.
Perfect.
We will give product updates, which we will publish also. And I hope I can come back later and be more specific on processes, designs, and things like that. I think it might be very interesting in this forum, at least.
Excellent. Thank you very much. And before I give the floor to Yariv, who is now preparing, I just want to remind everyone in the audience that there's a chance for you to ask questions in the chat. I've seen just a few so far, so there will be time for answering a few more than are already there. So let's move over, maybe back from mining to cities, and I assume a lot of that will be human waste, but we'll see what Yariv Cohen from EasyMining will tell us about the recycling of nutrients from cities to agriculture.
Thank you very much. My name is Yariv Cohen. I'm head of research and development at EasyMining. And I will talk, of course, about phosphorus, but I intend to expand a little bit and talk a little bit also on recycling of nitrogen and potassium from cities to agriculture. EasyMining is an innovation company within the RANKCELLS group. We are growing quite fast. We are now about 30 employees in EasyMining, and in the whole RANKCELLS group, we are, as you can see here, above 2,000 employees, and RANKCELLS is a large Swedish recycling company with operation in 4 different countries. In EasyMining, we work with the development of new technologies towards circular economy. We are now commercializing these 4 technologies that you can see here on the screen. We have the ash to phos, which is a process for phosphorus recovery from incinerated sludge ash. Ash to salt is a process to treat the fly ash from waste incineration, and it enables recovery of potassium. We have a cleanup. It's a technology for energy efficient production of ammonium phosphate, and we have a new technology for recovering of nitrogen. So with our technology, we cover the NPK, the main plant nutrients, and I will briefly talk a little bit about our technologies. If we start with ash to phos, it's about recovering phosphorus from sewage sludge, ash, more specifically. This Erik have shown you that there is an increase in sludge incineration. In this picture, you see the trend, and there are some countries to the left that there is a very high extent of incineration, and other countries that the extent of incineration is less. But the general trend is an increase in incineration of sewage sludge due to several reasons. And as Erik also mentioned, some countries have already taken a political decision that phosphorus recovery will be mandatory. It's Germany and Switzerland in the lead, which actually opened the market for recycling phosphorus from mainly ash of incinerated sewage sludge from these countries that the sludge is being incinerated in high extent. So our ambition is that if you incinerate the sludge, then the phosphorus ends up in the ash, and we would like to close the loop and to recover the phosphorus from the ash to enable reuse in agriculture. And of course, in this picture, you see to the left, you see that there is phosphorus coming into the loop from the mines, and there is a general problem in the world with the high cadmium and rhenium in rock phosphate. So one benefit also of recycling phosphorus from ash is that we can enable to get very pure products on the market and to reduce the health issues associated with such heavy metals. The ash to phos process is similar to processing of rock phosphate. It is a wet process in which we use acid to treat the ash, to dissolve the phosphorus, and as Lisbeth showed, you dissolve also all the metals that you have in the ash with acid. And with the ash to phos process, we used acid and lime as main input chemicals, and we can process the ash, recover the phosphorus in a clean form, separate the heavy metals for disposal. We can also recycle the iron and aluminium separately in a commercial form for reuse as coagulants in wastewater treatment plant. And then we have a residue from the leaching, which, as Lisbeth showed, can find a potential in cement and concrete industries. With the ash-to-phos process, a main feature is the detoxification, and here I just show you the degree of reduction in heavy metals. If we look at the heavy metal content in the initial ash and in the recovered product, you can see that we have, we can say about over 96. For many heavy metals, we are in 99, close to 100 reduction in concentration. So the phosphorus, the recovered phosphorus product is very clean. I would say it's the cleanest raw material available on the market today, independent on the ash composition. And from the process, we recover phosphorus in form of precipitated calcium phosphate, which we can use as for feed and for agricultural application, and also it can be converted to any kind of existing fertilizer such as ammonium phosphate or superphosphate and so on. In addition to that, we recover iron as ferric chloride for use in wastewater treatment. And we have several possibilities of recovering the aluminium as aluminium hydroxide, sodium aluminate, or A4 zeolite. And the residue, the silica sand, can find application in the cement and concrete industries. Here you can see some pictures from the pilot trials when scaling the technology. Currently, we work on two projects. One project is in Germany with we have a partnership with Gelsenwasser. It's a big German company that owns 60 wastewater treatment plants. Is now constructing 3 incinerators for incinerating the sludge. And we aim now to build the first ash-to-phos plant in Germany that you can see here in the picture with a capacity of 30,000 tons ash per year. It's about 3.5 million person equivalent per year. We are now in the status of doing the basic engineering for the plant, and the expected start of production is 2024. We have also a project in Sweden, in Helsingborg, and this is actually in the Kemira site. You can see there is an existing building. Historically, it's quite interesting because this building was a long time ago a phosphoric acid plant, and I think they probably used the apatite from Grängesberg in this plant before, but now we intend to put the ash-to-phos process into this existing building, and we aim for a capacity of 30,000 tons of ash per year. Since there is no Swedish ash, we intend to base the production on imported ash from outside of Sweden. We have finished the basic engineering for this plant and submitted the permit application and got also funding from the Swedish EPA for this plant. The expected time here is also 2024, 2025. Then I go over to talk a little bit about potassium, and this relates to our ash-to-salt technology, which is about treatment of fly ash from waste incinerators. And fly ash is a waste product that comes from the flue gas treatment when you incinerate wastes. And the main problem with the fly ash is that it has a very high salt content. In average in Sweden, there is about 20% of the weight is soluble salts, and this makes it very costly and difficult to dispose. It's a hazardous waste. In Sweden, we have around 300,000 tons of fly ash per year, and Ragn-Sells is handling about 50% of this market. And for that, we have developed the ash to salt process, which the process is about washing the fly ash with water, dissolving all the salts. We get some heavy metals. We have a heavy metal cleaning step in which we separate the heavy metal. And then this is a zero liquid discharge process. We crystallize the salts. We recover 3 salts: potassium chloride, calcium chloride, and sodium chloride. In the flue gas treatment, the incinerators add ammonia to reduce the NOx. So there is also ammonia in the ash, and we recover it in form of ammonium sulfate. And thereby we enable the residue to be either disposed in a non-hazardous landfill or to be recycled in the cement and concrete industries. We are now building the first plant. I think it's the biggest investment in circular economy in Sweden so far. Production is intended next year. The capacity of this plant will be 130,000 tons of fly ash per year. The ash will come from 15 incinerators and also from with conveyor from the nearby Aeon waste incinerator. The products from the plant will be potassium chloride that can be used for fertilizers or for chemical industries, sodium chloride and calcium chloride. All the products will come as solids with very high purity. In the picture you see the potassium chloride. And here you can see that there is very low heavy metal content. It's a very, very high quality product, and the LCA show also that the method is very favorable. And here I can just show you some picture from the building site. I think it's several months ago, these pictures, but you can see that the work is ongoing on the construction of the plant, and we expect the start of operation next year. And then I will go over to the last, talk a little bit about the recovering of nitrogen from wastewater. And this is our newest technology. Why is it important to recover nitrogen? The reason is that today nitrogen fertilizers are based on using natural gas to produce ammonia. In future, as LKAB showed, this can be changed, but today it is based on fossil fuel. And then when the nitrogen ends up in the wastewater, it is treated with a biological treatment which destroys the ammonia and release it as N2. And we would like, instead of using a biological treatment, to use a chemical treatment and not to destroy the nitrogen, but to recover it. And by that we can save a lot of greenhouse gases and energy and costs. The advantage of this process is that it's a chemical process. It is not sensitive to temperature, salinity, and so on. It has a fast kinetics. You don't need to have large basins and so on. It is based on a chemical reaction. We have a sorbent. You can see the white powder there that we add in a reactor and catch the nitrogen. And then we have a regeneration step in which we release the nitrogen, make a fertilizer, and reuse the sorbent. This project is an EU Life project with a budget of 3.6 million euro. We have several partners here. It's a Ragn-Sells, it's a Biofos, and Lantmännen. And we will build in this project a mobile container that will treat both landfill leachate and also will be moved to Biofos in Copenhagen to treat reject water from wastewater. Here you can see how the container looked like. We are now working with Covi on the detail engineering and we'll start in the fall to do the construction of the unit, and the first application will be landfill the leachate in Sweden. I think this is my last slide. I hope I managed to do it in the correct time. So thank you very much.
Great, thank you. So interesting that these plants, these new plants are now being built around the world. So a lot of things to look forward to and follow. Great. So now let's bring in all the different speakers because now it's time for the panel discussion. We have slightly more than 10 minutes and there are some questions from the audience already, so we're going to start with them. I have some additional questions as well, and there are plenty of things we could discuss, of course, if there's time for it. But I'm going to start to ask Ulrika something that came to me privately from Catherine Wretborn from Norion Mining. And she asks, what are the main environmental permits that are needed and which ones will take the longest to get? Can you say something about that?
Yes, I can. It's the apatite plants in Kiruna and Malmberget adjacent to our existing operations that takes the longest. They need to be part of the whole operation, so you reevaluate the whole operations in those areas. So that's why it takes so long to get them. And on the critical path, it's Malmberget because Kiruna is already ongoing. So those are the ones that takes the longest. For the industrial park, where we do the second part of the process, it's fairly okay with maybe 1.5 years of permit processing. But for Malmberget, it's several years.
Okay, yes, very long time periods that are needed. Now, Christer, I'm not sure you can read the chat, but there is a question for you.
Right.
Can you see the chat?
Yep.
So it's a matter of, the first part is, what do you mean by this 17% P?
Okay. Well, no, it's what we see from our process test. I can say that much, at least, that it's easy to extract the phosphorus in the form it is in the apatite. So there is no reaction with the iron. There is hematite, and predominantly hematite in the tailings also, but that we separate with high magnetic separator before we start flotation. I think Ulrika knows exactly what I'm talking about.
Yeah. Let me ask a question to Erik. In the end, you discussed very briefly that there's a lack of business models.
Yeah.
And I think there clearly is, because now suddenly actors need to go into new areas and sell products they didn't sell before. And there are new players coming up. So can you say something about that? What you see as main challenges there?
Yeah, I think that is still a young field, but I guess, for instance, what Jared presented from EasyMining, I think there are now links to the mineral fertilizer industry, if I'm not wrong. So there is probably a business model coming up, how these processes can be linked together. And you could use actually raw phosphorus for mineral production or fertilizer production, or in a traditional way, so to speak. But I guess at the same time, it's interesting to see that there's a lot of good ideas coming up to source separate or generate interesting nutrient-rich products, but it stays a little bit there. So there is still a gap to really have that into the agriculture in a proper way, because they have a lot of requirements. They don't want to build to buy new machines. They need to use their machines and everything. So there's a lot of work to be done there, actually. Still.
Thank you. Lisbeth, let me move to you. There's one thing that I reacted to. I agree with you that we could recover almost anything in the periodic system from these flows, but it's a matter of cost, right? And you didn't really touch upon that much. So what's reasonable to recover from using your technology?
Yeah, actually, I like that question because I was a bit sad there was things I forgot to say. And the first one was actually that I've been working with these electrochemical techniques for quite many years, and we've always been told that it's far too expensive to do these things because electricity is too expensive. But now things are really changing in the right direction here. And you could also say that this is an environmental friendly way to produce the assets because you're producing it inside, and you can take from solar cells and windmills, you have direct current anyway, so you could almost just plug it in. So I forgot to say that one. So the business case is changing tremendously positively in the way of the things that we are developing right now. I think, I admitted that I was working with 100 grams of ash, so I think it would not be very fair to say what it would cost, but I can tell you that we did a small business case together with Biophos on the sewage sludge ash and the phosphorus recovery with our method. And based on these laboratory results, we saw that it was really crucial that we could actually reuse the silicates, the particulate material afterwards, because if we had to deposit that at high costs after extracting the phosphorus, then we would only have the phosphorus price to pay for everything with. But if we could use all, both sell the phosphorus and the particulate matter for the industry, even give it for free. If it did not have a negative cost, then we could have a balance on the economy in this not very detailed but overview cost calculation. And since we did that, electricity has been even cheaper. So maybe it's even more favorable now. But I think also, we like not to deposit this as we work together also on using the silicates and in the construction materials. I think this is what can make the balance actually.
Yariv, let me ask a question to you as well. It's so interesting that you're planning to start these activities in Helsingborg. But the future for sewage sludge in Sweden is very unclear, and as Erik also told you about. So are you expecting a lot of sludge incineration in Sweden in the future? Do you know anything about the Swedish policies that I don't know? Because it's also unclear right now.
Yeah, this is my personal view. I expect that it will be incineration in Sweden. As you know, in Sweden, it's about 30% of the sludge that is used in agriculture, and there is no much more capacity to increase that. And if Sweden will have a requirement on phosphorus recycling, which is logical to have and to follow the whole Europe, then you have 70% of the sludge is actually not recycled and cannot be recycled by REVAC and spreading and Ragn-Sells spreading sludge. So we see that in future there will be a need for phosphorus recycling from ash in Sweden also. But as you know, in Sweden it's a big debate. It has been taking many years, and it's very, very slow, and Sweden is moving much slower than other countries in Europe, and we are focusing on Europe. But we believe that if we get a good business case and can make an investment based on imported ash to a plant in Sweden, we can later on use it for Swedish ash once the incineration in Sweden builds up. But of course the case should be built now on imported ash, and there will be a great demand for phosphorus recovery in Europe in future. So we don't see much problem to get the raw material to Helsingborg.
Right, thank you. Yariv, now some questions have appeared to you in the chat as well. Can you read the chat?
I didn't open it, but I
there's
guess
one
I can.
From Sudhanshu Pawar. Do you see any contaminants carried over to final product in ammonia recovery process?
For the nitrogen, No, we have if we install the technology from reject water, the heavy metal content in wastewater is very, very low. And we are having also a step to remove heavy metals if there is a need for that. So the recovered ammonia will be clean. This is the whole idea, to recover nutrients in a clean form.
And you also have a question from Katrin Wretborg from Norion Mining. Do you have cooperation with Fortum in Finland?
No, not at the moment.
Okay. So time is almost up. Is there anything, if I give you just one sentence each to say as a final message to the audience now, each of you, what would you like to share? Can we start in the order that you presented, maybe? Ulrika, I know this is difficult. What one sentence would you want to tell us now after this session?
Well, I see a lot of opportunities that we can recover and recycle large amounts of phosphorus and other critical materials by this group from Sweden. So we have great opportunities.
Right. Thank you. Erik, what do you say?
Well, I can say that I hope that I think it was a good picture you showed, Magdalena, with different sources of phosphorus, but we shouldn't forget if the sewage part is quite small in comparison, it still has a lot of other good effects if we are recycling that. So don't forget that.
That's a very good point. Lisbeth, what's your final message?
Well, it will be a personal one, because it will simply be, I'm just so happy that things are happening, you know, that we see full scale and we see a lot of responsibility and a lot of goodwill. I think this is so important, because I think we've heard about major real life steps from the university perspective, and I think that is really important, really nice. And I was very happy to hear these initiatives that we've heard about.
Me too. And Christer, your final words.
Well, I think we are in very unique times. What we see now is have never happened. We are, as a nation, Sweden, in this case, very fortunate, because we have the opportunity to contribute. As we have been discussing today, there are a lot of circular resources available, and for us in Grängesberg, I mean, I hope that our Apatite project will be the starting for a new future of this region, this very important, proud region of mining.
Thank you, Christer. Yariv, final words from you.
Yes, I think it's an exciting time. I have been working many years with these issues, and there have been a lot of talking, but now we see action. But still, we need more action. There are we need, for instance, in Sweden, a political decision that to recover phosphorus, we need to take this decision. It's too long without any decision. Another thing is that, for instance, to use recovered phosphorus for feed application, it's not allowed in Europe due to the origin and not the quality. This is completely wrong. We should have regulation based on the quality and not the origin. So we need actually to work in politics and in regulation and legislation and end of waste criteria and so on to actually help this transition to circular economy. But we are on the way, and we will make it.
Thank you. And I think all of us will be involved in this future work, and also, of course, very interested in continuing the discussions in this area. Thank you so much to all the presenters in this session, and thank you all also to the participants who listened, and do contact the presenters if you have additional questions. Thank you very much. This session is now over, and hopefully we'll get to discuss this much more in the future, but bye for now. Thanks.
Thank you.
Bye.
Bye-bye.